So now we have built a baseline model. Baseline model provides us a good starting point, but then we have to do some more improvements in our model. One problem that was common and still is common in deep learning models is overfitting. Overfitting is also evident in our baseline model. If we look at the loss, the validation loss in the output of our model, it is increasing, which indicates that there might be overfitting in our model. Overfitting, what essentially means is we might have a bias in the model towards the training data. To overcome this overfitting problem, several things were tried. A common approach to solve overfitting is regularization techniques such as L1 and L2. But those regularization techniques did not work well with deep learning models. It was becoming a major problem, and this problem was due to a phenomenon called co-adaptation in deep learning networks, which was finally resolved with the advent of a concept called dropout. Now we are going to learn about first the problem of co-adaptation, which was causing this overfitting issue or model learning issue in deep learning, and then we'll talk about how dropout resolves it. So starting with co-adaptation. This is again our typical representation of a MLP network. Now consider any node in this network. Let's take this node and expand it here. So expanding means, let me just elongate the orange node that I had like this. Now inside this orange node, the node I selected, I am having m number of connections getting in. Suppose m is the number of nodes present in my prior layer, then all of these nodes are going to send one connection or make one connection with this orange node. So I have m connections that get into this. Make it this. And this orange node is then connected with my output node. Let me highlight it with green. So I have this green final node here that it emits to. Make the connections with green as well. The reason I'm using a different color for these connections is for our further discussion on co-adaptation and dropout, these are not important. Let's focus on these connections in black lines. Also, to make it look a little better, I'll just put some circles here. They're symbolic, they do not have much meaning here. Okay, so I expanded this orange selected node like this, and now I have all the weights that are incoming into this. Let me call them W1, W2, W3, and Wn. What happens if is, this is usually big network, and with too many connections, some of these connections will become more important than the other. So it might happen that W1 and W2 became very big, like large numbers, meaning they became very strong connections. And these are, suppose, very small, could not make much impact. And the fact that W1 and W2 became large could be, the reason for that could be as simple as the random initialization that happened for that training. So W1 and W2 can take large values either due to random initialization, or they might be truly more important than the bottom weights. No matter what the case is, if this happens during the learning iterations, during the training, these became very important. Gradually, they start to suppress all other connections, meaning they become strong when we are learning again. To re-emphasize or to reiterate, we learn through epochs and within epochs over batches. During all of these learning iterations, the strong will get stronger and the weak gets weaker. So this is a problem with society as well sometimes. But this also became a problem for deep learning. And this is what is called as co-adaptation. In co-adaptation, what happens is the weak nodes, which are here, in the presence of these strong nodes, over time they stop participating because these strong nodes or heavy nodes, they are doing all the weightlifting anyway. They are doing the job of making predictions. Then as the model keeps on learning, it only focuses on updating these weights and they start ignoring these weaker weights. So if it started as a weak node, it is likely to stay as a weak node till the end of the training. And this co-adaptation issue causes major problem because due to co-adaptation, if I make a larger network, suppose I increased this layer from M to say M prime, where M prime is bigger than M, say I made it 2 times M. Now I have 2 times as many nodes, which means I will have 2 times as many connections getting into this orange node. But if still these 2 connections are the most important or they are more stronger, no matter how many connections I'm gonna add, they'll still not participate, and making the model larger does not really help. And this became a major limitation for deep learning networks. We could not leverage the size of the model. Even the traditional regularization technique that were at the time L1 and L2, they did not help much because these techniques, they are also data driven and rely on the magnitude of these weights. For example, let's consider L1. L1 would also keep these these connections as active, these weights as active, while L1 will push these bottom weak ones to 0. And same thing will happen with L2. So all in all, co-adaptation became a major issue. It limited our ability to increase or leverage the ability of deep learning model by changing its size or expanding its size, which was later addressed by Dropout, which we are going to learn in the next part.